Hi, welcome to Solving Science episode 20. Wow, it's a big one. We're solving problems that are emerging from CERN, only the largest man-made human experiment of physics in the entire world. And they're issuing reports and data that they can't understand, they can't explain. And I think expanse tension theory can. So in this video, I'm going to talk through what happens when you smash lead atoms into each other at near light speed. I'm going to explain why the results that have been produced are not explained by current science or physics. And then I'm going to bring in a causal explanation using general expanse tension theory. And hopefully you'll see that the alignment between what CERN have produced and what expanse tension theory can explain and predict come into perfect alignment. So hold on, it's a big one, it's coming out of CERN. So, two experiments, Alice and Atlas, they're smashing lead nuclei into each other, at near light speed. These are not mere particle collisions, they're forming the hottest, most dense material ever produced on the planet. Those of you who've been watching this will pick up the word densest. No, densest. Because general expanse tension theory is a density-dependent theory. Now, if we're producing at CERN a dense environment, well, general expanse tension theory may plausibly have something to say about that. Hold that thought. So they're creating a quark-gluon plasma similar to conditions just after the Big Bang. Physicists then measure how this material expands and cools, and the key point here is they didn't just measure where the particles go, they measure how momentum is redistributed across the entire event. Now, Alice and Atlas experiments saw something completely new. They found long-range transverse momentum correlations. And that means that the particles at the outward end of this collision, far apart from each other, behave as if they're part of the same expanding system, acting like a fluid in a medium. Okay, so if you've been watching expanse tension theory, you're already following where this is going. So the exciting part is two lead atoms colliding, you expect a collision, but this material was accelerating outwardly in a collective, organized manner. Completely unexplained causally. Not just flying apart from the collision energy, but beyond that, something else was driving an acceleration. And it's as if it's this medium itself is driving its expansion. The effect is isotropic. It's the same in all directions. It's event-wide, involving the whole system, and it's density sensitive. Okay. Now, CERN scientists were very clear. The behaviour they saw was real and measurable and statistically valid, but it's not yet causally explained. We don't know why this is happening. So to be clear, doesn't mean any of our existing physics are wrong. It's just we haven't got to the depth of physics to explain causally what's absolutely happening. Okay, so what's missing here is simply a causal gap. Now, if we introduce expanse tension theory into this, we have, hopefully if you're watching the channel, we have a real all-pervading, gauge-invariant, singlet scalar field which couples to the Higgs portal with continuous density-dependent modulation. It's complicated. It just says when the density falls below certain thresholds, matter and the expansion field of the universe can couple together, and we've said how that can explain dark matter, or it can uncouple, and we've said how that can explain dark energy and expansion coefficients and the Hubble tension. But actually, we've also shown with the Thomas Young double slit experiment and with Richard Feynman glass reflection paradox, this is also happening at the atomic and subatomic scales as well. So this isn't dark energy, dark matter. We dismiss those ideas. We're explaining those ideas. But the key feature here is the density dependence of expanse tension theory. So under general expanse tension theory, it's that density that matters, and it modulates how expansion itself responds. There's no extra energy, it's no violation of conservation laws of energy, and there's no need to modify quantum field theory or quantum chromodynamics or any existing science. Okay, so when I applied general expanse tension theory to these exact results from CERN, the alignment was striking. I'm going to read this carefully. Okay, so what general expanse tension theory naturally predicts is the isotropic expansion effects seen, the event-wide momentum redistribution, sensitivity to density, a mass-dependent response, and long-range correlations, i.e. the acceleration without the injection of energy. And that's what expanse tension theory would give us. This is not particles being pushed harder. It's the medium responding differently because the density threshold was crossed. That's exactly what Alice and Atlas at CERN observed and reported. So I've got a paper. I'm going to link to it with this video. It's in Zenodo. You can go and access it and read it and download it. I'm not claiming that it's proof, or I'm not fitting any parameters. I'm not reinterpreting any CERN results. I'm purely taking the results and saying, can expanse tension theory, a density-dependent scalar field that couples with Higgs licence mass, explain the acceleration of radial outward flow that we see from CERN? And the alignment is flawless, frankly. So the paper goes through every single observed phenomena in this lead-lead atom collision, and what is observed aligns with what expanse tension theory predicts. Okay, so exciting. It's the dream come true of any physicist to take a theory and apply it. And at the moment we have the alignment of theory explanatory power with empirical observation. So please take a look at the paper. It's an exciting one. The idea that general expanse tension theory can immediately provide causal explanation for an immediate live experiment running at CERN right now with reports coming out. This is exciting physics. Okay, so density dependent general expanse tension theory explains the acceleration of radial outflow from lead-lead nuclei collisions at CERN. Okay, leave me some feedback, please. Thank you. Please subscribe and follow the channel if you're excited to move beyond chasing dark matter and dark energy and other kind of nonsense. Okay, bye-bye.